Hi everybody, and welcome to our unit on reaction rates and equilibrium. So this unit is really broken into two parts, and the first one deals with reaction rates. All right, we're going to be taking a closer look at the speed at which a reaction takes place, and that's known as the rate of reaction. All right, the rate is usually expressed as amount of reactant changing per unit time. It could also be the amount of product changing per unit time, but we'll look at that as we move further. All right, before we talk about actual rates, we want to talk about the process of a reaction. We've certainly looked at a lot of different types of chemical reactions, but we really haven't looked into what is going on with that reaction, okay? So for a reaction to occur, the first thing that has to happen is that the reactants actually have to come into contact with each other. They actually have to hit each other. And this is what's known as collision theory, all right? In order for this to happen, all right, they not only just have to hit into each other, but they have to hit into each other with enough energy. And Ke stands for kinetic energy. That's the energy of motion. All right. And the activation energy the activation energy is the minimum amount of energy that colliding particles must have in order to react. And this is just going to really depend on what your reactants are. Some of them have a very low activation energy and will react very, very quickly. Some of them have higher activation energies, and energy actually has to be added to the reaction in order for it to go. All right. Once you have that that appropriate activation energy and the particles are colliding, you will get what is known as an activated complex. And the activated complex is an unstable arrangement of atoms, all right, that actually are ready to form and reform bonds, okay? It's at the peak of that activation energy, and two things can happen once you have that activated complex, all right? The activated complex can actually become your product, all right? So it can end in two ways. It can become the product, which is typically what we want it to do, but it also has the ability to go back and become the original reactants. All right. So we're going to take a look at a graph to show us this activation energy and this activated complex. And this graph is known as a potential energy graph. This is kind of one of the classic graphs in chemistry. And I want you to draw this out with me. Okay, so it is going to be a graph. And of course, yours should look a little bit nicer than mine because my handwriting's not great. All right, so on your y-axis, you have energy. Okay. On the x-axis, there's lots of different kind of representations of the x-axis. I think the easiest thing to kind of think of the x-axis is just time. Okay, so what's happening over time? Technically, it's supposed to be what's called a reaction coordinate, but that's really not very helpful for people. So we'll just kind of think of it as reaction progression, all right, because that can be a little bit more. Okay, reaction progression. So here we go. I am going to have my reactants are going to start at a certain energy, whatever that energy may be. Okay, and those are my reactants, and my reactant, I'll write over here. So reactant, we'll call A. All right, that reactant, we're going to add some energy to it, so it becomes the activated complex. Okay, so here we go, activated complex. Okay. All right, it's not going to stay up at that high energy for long. It will then go back down, and then we will get our products. Okay, so here we go at A, which is our reactant, and we are forming our product, which we'll just call B. Okay, so there are my products. All right, so there's a couple important things that you need to note. First off, the top of my peak here is my activated complex. All right. Then there's a couple different energies that are important to us, okay? The energy that it takes for my reactants to get up to that activated complex right here, all right, that is called the activation energy and gets the abbreviation EA. All right. The difference in energy between where my reactants start and my products end, all right, so I'll just put that little arrow right here. So between A and B is called your delta H, otherwise known, here's supposed to be a delta. I always have a hard time typing those. So that's a delta H, your change in enthalpy. Enthalpy is a word in chemistry that we use for energy. So it's fine to think of it as a change in energy. So this is your enthalpy of reaction. Now, here's an important part, okay? If you notice, your reactants started at a higher energy, your y-axis is your energy, your reactants started at a higher energy than your products. So we gave off energy here, which would mean that our delta H gets a negative value. All right, so let's take a look at this again. So for this reaction, your products are at a lower energy than your reactants. This tells you two things. Your reaction is what we call exothermic. All right, which means it gives off energy. If you were actually holding the container where this reaction was occurring, and as this reaction goes, the container would actually be warm because it's giving off energy to the environment. All right, and your delta H, as we set up here, has a negative value. All right, negative, not so much in the math thing, the math way of negative, but that negative sign tells us that I'm giving off energy. I am producing energy. All right, so again, potential energy graph, we're definitely going to do some practice with that. That is a potential energy graph for an exothermic reaction. Now let's take a look at one for an opposite type of reaction. All right, still our same situation here. Okay, and for this one, we're going to go say that this reaction is for C to D, C being my reactant, D being my product. All right, energy is still, okay, on my y-axis. Okay. But this time you're going to notice the graph looks a little bit different. All right, there we go. So C is starting here. Up here is my activated complex. My products end up here. All right, if I were to label this, the distance from my activated complex to where my reactant started, remember that is my activation energy. The change in energy here from reactant to product is my delta H. In this reaction, though, if you note, my reactants started at a lower energy than my products. This reaction is actually gaining energy from the environment. And when that happens, this, we call it an endothermic reaction. Remember, our abbreviation for reaction is RXN. All right, our delta H, remember that is a delta. Delta H has a positive value. And that tells you that energy is being taken in. Okay, great. As I mentioned, we're going to do a lot of practice with these potential energy graphs because they give us a lot of great information. We also want to look, again, a little bit deeper into what's going on with the rate of reaction, how quickly a reaction takes place. All right, and there's 5 factors that affect the rate of reaction. First, and certainly what we can think of as most important, is the nature of our reactants. What are our reactants made of? Certain compounds, certain elements are just going to react quicker because of what's going on with that element. The second is the concentration of reactants. All right, we are going to be talking about concentration in terms of molarity, so we should be comfortable with that. In general, now this is in general because there are some exceptions. In general, an increase in concentration will increase your rate of reaction because you have more particles and they're going to be able to collide more readily with each other. But this must be determined experimentally, and we're going to actually take a look at that. So that's super important. Concentration are only used for if we're dealing with gases and solutions. For pure liquids and pure solids, we really don't have a situation of concentration, but we'll talk more about that as time goes on. Temperature. Temperature, remember, is a measure of kinetic energy, of the average kinetic energy. An increase in temperature will always raise the rate of reaction, okay? At higher temperatures, more particles will have that necessary activation energy. In general, for every 10 degrees Celsius increase in temp, the rate of reaction will double. The fourth is surface area. Typically, the surface area, if you increase that, you will have a greater rate of reaction. This, again, is just giving you more particles to be able to touch, come into contact with each other more readily. All right. The fifth factor is the presence of a catalyst. A catalyst is a substance that speeds up the rate of reaction by lowering the activation energy. And we're going to take a look at that right here in this graph. All right, so this is another potential energy graph. Here's my energy. Here's this one's calling it course of reaction. That's another nice way of saying it. All right, and it's a little hard to see as far as, because this is in black and white, but this top line here is just your uncatalyzed, your regular reaction. And we can see our activation energy is from where our reactant started, which they've just extended that line, up until the peak of that curve. When a catalyst is added, all right, that lowers that activation energy. Okay. So a catalyst is something that is added to a reaction to speed that reaction up, but it itself is not used up in that reaction. So what makes catalysts so great is that they are reusable. They can be used over and over again. All right. Also note, okay, catalysts change the activation energy. They do not, however, and this is a change in G. We'll just think of this as a delta H to make our lives a little simpler. All right. They don't, however, change the delta H. Your enthalpy of reaction will still be the same. It's the activation energy that changes. So let's take a look at a catalyst in action here. All right. And this is an example of ozone depletion. Okay. And ozone depletion is a catalyzed reaction. Okay, so let's just take a quick look. Here we go. We have O here, and you might think that looks strange. You told me that O's couldn't be all by themselves. Well, they can't where we are on Earth, but up in the atmosphere, you can have what are known as free radicals, and that can happen. All right, and when those free radicals hit ozone, this is what ozone is, it's O3, it breaks down that O3 to give us oxygen gas. And again, for our ozone layer that protects us from ultraviolet radiation, this is not a great reaction to happen. Okay, why is this reaction happening as quickly as it does, and how are we having an impact on it? Well, it's because of the nitrous oxide that we produce as a greenhouse gas. So let's take a look at this reaction. This up here is what is known as the overall reaction. These are your starting reactants. This is your end product. Reactions, however, don't always take place in just one boom step. Oftentimes they take more than one step. And what's really happening here is that your ozone, all right, is reacting with nitrogen monoxide to give us nitrogen dioxide, all right, plus oxygen gas. And then our free radical reacts with that NO2 to give us NO, again, nitrogen monoxide, and some more oxygen gas. So let's take a look at why are all of these nitrogen compounds in this is what's called a mechanism, but it's not in the overall reaction. To get the overall reaction, we have to take away anything that appears exactly the same on both sides. So kind of like a math problem, kind of like when we were doing before those net ionic equations. So let's see what occurs exactly the same on both sides. Well, O3 is on the left. I don't have any O3 on the right. NO is on the left and on the right. And NO2 is on the left and on the right. So those are not going to end up in our overall reaction. And if we write what's left over after we take away those, what do I get is O plus O3 giving us O2 and O2, which is 2O2. That's our overall. Well, what are these things, this NO and this NO2? Well, they're going to be either an intermediate or a catalyst that we were talking about. So let's take a look. An intermediate is a substance that is produced and then used up within the reaction. So for an intermediate, here's the clue. The first place you're going to see it is as a product, and then the second place is as a reactant because it is produced and then it is used up. So in our example, that's going to be NO2. These are always going to be written in order for you, so don't worry about that. The first place you see it is the product, then it is used up. A catalyst is a substance that has been unchanged throughout the reaction. Again, here's your clue. The first place you're going to see this one is on the reactant side, and then the last place you see it is on the product. Because we use a catalyst to speed the reaction up, but we get that catalyst back at the end. So our catalyst here is NO. All right. So again, just to recap, an intermediate is first produced, then used up. Catalyst, first you're going to see it as a reactant. The final place you'll see it is a product. And again, we will do some practice with this as well. Okay. Last up, let's talk about our different types of catalysts. We can have what are known as homogeneous catalysts, and a homogeneous catalyst, all that means is it's the same state as the reactants. So in our ozone example, all of those were gases. All right, so in that case, our nitrogen monoxide, our NO, is considered a homogeneous catalyst. You can also have heterogeneous catalysts. And heterogeneous catalysts are in a different state as the reactants. Oftentimes, you will have a heterogeneous catalyst when dealing with gases, and that catalyst will be a metal. An example is in combustion engine cars, we have what are known as catalytic converters. And these converters actually have platinum metal, and they're used to be a catalyst for certain reactions to try and reduce those greenhouse gases. All right, so, two last terms when dealing with catalysts. Enzymes are types of catalysts. They are biological catalysts, and I know you all talked about that last year in biology, and they are very important. Remember, a catalyst is there to speed up a reaction. Well, we do have substances that are the opposite of catalysts, and those are known as inhibitors. A substance that interferes with the catalyst and therefore will slow the reaction down. All right, we're going to do some practice with this. Take care. Have a great day.